I want you to picture something for me. Think of a NASA spacecraft, specifically the 2006 NASA ST-5.
Oh, yeah. The ST5.
Right. So picture its communication antenna. I mean, if
Right.
you're imagining a sleek, symmetrical satellite dish, or
Yeah.
maybe a perfectly straight metal rod.
Like what a normal human engineer would build.
Exactly. You're visualizing traditional design. But the ST-5 antenna looks bizarre. It looks like a twisted, mangled paperclip.
It really does.
It's jagged. It's asymmetrical. To the untrained eye, it honestly looks like a manufacturing mistake. But human engineers did not design that shape.
They didn't. And the computer that generated that shape didn't strictly design it either, at least not in the traditional top-down sense we usually associate with engineering.
Right.
It actually evolved it. It ran a program that simulated millions of generations of tiny random changes until the absolute optimal shape for broadcasting a signal just naturally emerged.
It's just wild to think about. It completely challenges our basic assumptions about how technology is created. I mean, we are talking about biological code here.
Yeah, it's a fascinating concept.
So today, our mission on this deep dive is to unpack the Wikipedia article on genetic algorithms. We're going to explore how computer science borrows the rules of natural selection, like Charles Darwin's playbook, to solve these staggeringly complex problems.
Right, because you see these algorithms applied all over the place, like hyperparameter optimization.
Which is essentially tuning the complex dials of an AI model so it learns efficiently, right?
Exactly. Or they're used in causal inference, which is the process of untangling actual cause and effect relationships from massive, messy piles of data.
So for you listening, whether you're a coder or just someone fascinated by how nature inspires tech, this deep dive is going to give you a pretty powerful new mental model for problem solving. But before we get too far into the weeds, what exactly is a genetic algorithm?
Well, a genetic algorithm, or a GA, is a specific type of metaheuristic.
Metaheuristic, okay.
Right. In computer science, a metaheuristic is basically a higher-level procedure designed to find a good enough solution to an optimization problem, especially when you have incomplete information or, limited computing capacity.
Got it. So when the problem is just too big.
Exactly. When you have a massive problem space, meaning there are so many possible solutions that a computer couldn't possibly check them all one by one, a GA searches that space using biologically inspired operators.
Biologically inspired operators. Like what?
Things like selection, crossover, and mutation.
Okay, but here's the fascinating tension we need to explore today. While NASA is flying these evolved designs in outer space and logistics companies use them to route trucks, some highly respected computer scientists absolutely despise them.
Oh, yeah. The haters are very vocal.
Right. The source material features this notoriously harsh critique from Steven Scanna. He's the author of the widely read Algorithm Design Manual, and he famously calls this entire approach pseudobiology voodoo.
Voodoo. That's a strong word.
He actively warns programmers to stay away from it. So as we walk through how this works, we need to figure out who is right. Is this a profound tool or just pseudoscientific hype?
That's a great lens for this discussion. To evaluate Scanna's claim that it's just voodoo, we really have to look at the actual mechanics of the algorithm. We have to see how you actually encode evolution.
Right. How do you code Charles Darwin?
Well, it begins with creating a sort of digital Galapagos. We start with a phase called initialization. The algorithm generates a massive population of completely random candidate solutions.
So like the first generation of digital organisms.
Exactly. And traditionally, the properties of these candidates, their chromosomes or genotypes, if we're keeping the biology metaphor, are represented simply as strings of binary code.
Just strings of ones and zeros.
Just ones and zeros.
I mentioned most of those random first-generation organisms are going to be absolutely terrible at whatever problem we're trying to solve. I mean, if you randomly mash together a shape for an antenna, it probably won't broadcast a signal at all.
Oh, they're completely useless. That is the expected outcome for generation 1. But that brings us to the next critical step, which is the fitness function.
The fitness function.
We have to evaluate every single individual in that generation to see how fit they are. The fitness function acts as the harsh environment that decides who lives and who dies.
Let's ground this in a concrete example from the source material so you can really visualize the math here. There's a classic computer science puzzle called the knapsack problem.
Oh, that's a perfect example.
Right. So imagine you have a backpack, and it has a strict weight limit, let's say 15 pounds. And you have a collection of items you could put inside. each with a different weight and a different monetary value.
Right.
So you have a lightweight first aid kit that's highly valuable, a heavy cast iron pan that's worth very little, maybe a moderately heavy tent that's very valuable, and so on. Your goal is to maximize the monetary value inside the bag without exceeding that 15-pound limit and ripping the bag apart.
Right. So using a genetic algorithm to solve this means every candidate solution is represented by one of those binary strings.
Hell yeah.
Each slot in the string represents a specific item from your collection. So a 1 in the first slot means the first aid kit goes into the backpack. A 0 in the second slot means the cast iron pan stays out.
Okay, so the fitness function comes along and looks at a specific binary string, say 101. It adds up the weight of the items represented by the ones.
Exactly.
And if the total weight is like 20 pounds, which exceeds your 15-pound capacity, what happens?
Your fitness score drops to 0. That digital organism is dead. It failed the environment test.
Wow. Brutal.
Very. But if the weight is under the limit, your fitness score becomes the combined monetary value of those specific items.
Okay, so we've got our scores. What happens to the survivors?
Once every candidate in that first generation is scored, the algorithm moves to the selection phase. It stochastically selects the individuals with the highest fitness scores.
Stochastically, meaning randomly.
Yes, but a weighted random process. Picture a loaded roulette wheel.
Okay.
The candidates with the highest fitness scores get the widest slots on the wheel. So they aren't guaranteed to be selected, but the odds are heavily in their favor. The fittest survive.
Got it.
And then we apply genetic operators to create the second generation. The primary operator is crossover or recombination.
This is where it gets really cool. The crossover phase is where the algorithm actually builds something new. Instead of just picking a winner, it combines them.
It's exactly.
I always think of it like breeding a champion racehorse, right?
Mm-hmm.
You take the endurance of one parent and the speed of another. Or imagine taking two different Lego vehicles.
Okay, Legos.
Yeah. You have a race car that scored high for speed and a monster truck that scored high for durability. You snap both of them in half down the middle, and you push the front half of the race car onto the back wheels of the monster truck.
That Lego analogy perfectly illustrates the mechanical splicing. With binary strings, the computer literally slices the 1 and 0 sequences of two successful parents at a random midpoint and splices them together to make a child chromosome.
Wow. Literally cutting the code in half.
Right. The assumption is that by combining the genetic material of two strong performers, the resulting child might inherit the best traits of both and achieve an even higher fitness score.
But wait, if we just take the front half of the race car and the back half of the truck and we just keep recombining those same successful parts over and over across hundreds of generations, wouldn't we eventually hit a wall?
Yes.
Like the population would just become a monoculture of identical clones? Isn't that just digital inbreeding? The algorithm would run out of new ideas?
That is a fundamental vulnerability. It's known as premature convergence. The algorithm gets stuck because it exhausted its genetic diversity too early.
So how do you fix that?
To prevent this, developers rely on the second genetic operator, which is mutation.
Mutation.
Right. Just as ultraviolet light might cause a mutation in biological DNA, the computer occasionally flips a bit at random while copying the genetic code to the child.
So a 1 becomes a 0.
Or a 0 becomes a 1. Exactly.
So going back to the analogies, a random item gets thrown into the backpack, or a random piece of Lego gets swapped out, introducing a completely new trait that wasn't present in either parent.
Yes. And developers also implement rules like the speciation heuristic to actively fight that monoculture.
Speciation heuristic, what does that do?
This rule mathematically analyzes the population and penalizes crossover between candidate solutions that are too genetically similar to each other.
Oh, no.
Yeah, it effectively forces the population to remain diverse by making sure distant cousins breed rather than siblings.
That's incredibly clever.
It is. And interestingly, while using two parents is the most intuitive, biologically inspired method, the research notes something wild. Some algorithms generate much higher quality chromosomes by pulling genetic material from 3 or 4 parents to create a single child.
Okay, now that is a place where computer science definitely leaves biology behind. We don't see 4-parent organisms in nature.
Very true.
So we know the mechanics now. Selection, crossover, mutation. But we still need to address the underlying logic. Why does a random mashup of 1s and 0s actually result in a brilliantly engineered spacecraft antenna instead of a pile of useless digital junk?
Right, it seems like magic. But to understand the logic, we look to the building block hypothesis. This was proposed by John Holland in the 1970s.
Okay.
Holland suggested that genetic algorithms don't just blindly stumble into a massive, perfectly formed answer all at once. Instead, they operate by identifying and recombining what he called schemata.
Schemata, like pieces of a schema.
Exactly. These are short, low-order partial solutions, just tiny fragments of the binary string that happen to offer a slight fitness advantage.
The text actually includes a great quote from David E. Goldberg that visualizes this perfectly. He wrote, just as a child creates magnificent fortresses through the arrangement of simple blocks of wood, so does a genetic algorithm seek near optimal performance through the juxtaposition of short, low-order, high-performance schemata.
That's the core of it. The algorithm might discover through random mutation that a specific sequence of just 3 bits works remarkably well for the base of our antenna.
Right.
Simultaneously, in a totally different part of the population, it discovers a sequence of 4 bits that works well for the tip of the antenna. Over successive generations, through crossover, those two high-performing building blocks naturally find each other and snap together.
Wow. But we're talking about combining hundreds or thousands of these tiny building block schemata over millions of generations to form something as complex as an antenna.
Yes.
That sounds computationally exhausting. I mean,
Right.
at what point does the sheer math of running this simulation outweigh the benefits?
And that brings us to the severe limitations of this approach. It really begins to explain why critics like Stephen Skeena are so wary of it.
Right, the voodoo guy.
Exactly, because evaluating a digital backpack is instantaneous. But imagine a structural optimization problem, like evolving the aerodynamic shape of a vehicle.
Oh, man.
Yeah. A single fitness evaluation there requires running a computational fluid dynamics simulation, which means simulating how air flows over every square millimeter of a 3D shape in real time.
So testing just one candidate solution might take, what, hours?
Hours or even days on a supercomputer.
Just for one. If a single generation has 1,000 candidates, and you need to run thousands of generations to evolve a good design, that process would literally take years.
Exactly. Genetic algorithms simply do not scale well with massive complexity because the search space explodes exponentially. This is why you might see an evolutionary algorithm used to encode the design for a single fan blade, but you would never use it to evolve the design for an entire jet engine.
The computational cost is just astronomical.
Way too high.
The sources also point out another massive flaw in how these algorithms navigate their problem space. They're incredibly vulnerable to getting trapped on what is called a local optima.
Right, the local optima trap. Picture the fitness landscape as a vast mountain range. Your goal is to reach the absolute highest peak, the global optimum.
The Mount Everest of solutions.
Yes, but a genetic algorithm operates somewhat like a blindfolded climber. It's very good at feeling the slope of the ground directly under its feet and walking uphill, but it has no vision of the broader landscape.
Okay, I see where this is going.
It might climb up the nearest, smallest hill. Once it reaches the top of that small hill, any step it takes in any direction goes downward.
So the algorithm assumes it's finished the job.
Yeah.
Found the peak.
Right. It doesn't realize there is a massive Mount Everest sitting just 1 mile away, because getting to Mount Everest would require walking down into the valley first. It doesn't know how to sacrifice short-term fitness for long-term gains.
So it's stuck on a molehill thinking it's on Everest. Which brings us fully back to Stephen Skiena's critique in the Algorithm Design Manual. He argues that modeling applications with genetic operators on bit strings is, in his words, quite unnatural.
He really doesn't pull his punches.
He believes the pseudobiology adds an unnecessary layer of complexity between the programmer and the actual problem. He recommends abandoning Darwin entirely and sticking to what he calls simulated annealing for heuristic search needs.
Right.
And simulated annealing borrows its logic from metallurgy rather than
Right.
biology, right?
It does. It's inspired by the controlled cooling of materials to reduce structural defects. Simulated annealing introduces a temperature parameter to the search process.
The temperature parameter, how does that work?
When the temperature is artificially high at the start of the algorithm, it's programmed to frequently accept worse solutions. Going back to our blindfolded climber, a high temperature means the climber is willing to wander downhill into the valleys,
Oh,
which allows them to escape those small local hills. Exactly. And as the algorithm runs, the temperature slowly cools down and the climber becomes more strictly focused on climbing purely upward. Skeena vastly prefers this mathematical thermodynamic approach over tracking digital chromosomes.
okay. He calls genetic algorithms voodoo. but we know for a fact they're successfully used out in the wild. I mean, the source lists them being used to schedule incredibly complex timetables, design aerodynamic bodies, and generate walking methods for computer-animated figures.
They absolutely are.
So if Skeena's criticisms about premature convergence and getting stuck on local hills are valid, how do modern developers actually fix those flaws to make these algorithms work?
Well, they fix them by evolving the algorithm itself. Developers have created powerful variants of the standard genetic algorithm to address every one of Skeena's points.
Oh, like a meta-evolution.
Pretty much. Let's look at elitism, for example. In a standard crossover and mutation process, there's always a mathematical risk that you accidentally destroy your absolute best solution while trying to breed it.
Like you mutate the one perfect gene it had?
Exactly. Elitism is a variant rule that mandates the absolute fittest organism, or maybe a small group of the best, is carried over to the next generation completely unaltered. It guarantees your solution quality will never drop from one generation to the next.
You essentially keep your champion safe on the sidelines, preserving that perfect genetic sequence, while the rest of the population continues to breed and mutate.
Right.
What about the problem of the algorithm losing its diversity and getting stuck on a small hill?
Developers solve that with adaptive genetic algorithms, or AGAs. In an early basic GA, a programmer might hard-code the mutation rate at a fixed 1%, but an adaptive GA monitors its own progress.
It watches itself.
Yeah, it adaptively adjusts the probabilities of crossover and mutation on the fly based on the population's current fitness landscape.
That is brilliant. It's like a video game adjusting its own difficulty behind the scenes.
Oh, exactly like that.
The algorithm senses that every organism in the population is becoming too genetically similar, which means they're likely stuck on a local hill. So it automatically cranks up the mutation dial to 10 or 20%.
Right. It forces a wave of weird, highly diverse children into the environment to see if one of those radical mutations happens to land on the slope of a bigger mountain.
It's just so elegant.
They also implement structural fixes for how the chromosomes themselves are written. The text highlights a technique called gray coding, which solves a critical mathematical trap known as a Hamming wall.
Walk us through the mechanics of a Hamming wall, because this gets to the core of why binary code can be so tricky for evolution.
Okay, so in standard binary code, numbers are represented by patterns of ones and zeros. The number 7 is written as 0, 1, 1, 1.
0, 1, 1, 1.
And the number 8 is written as 1, 0, 0, 0.
Wait, so every single digit flips?
Exactly. If your digital organism is currently at a fitness level of 7 and the environment demands it evolve to an 8, the algorithm has to flip 4 separate bits perfectly and simultaneously. It has to change that 0 to a 1 and all 3 ones to zeros.
If it relies on random mutation, the odds of flipping 4 specific bits at the exact same time are incredibly low.
Extremely low.
If it only flips 3 of them, it might land on, like, the number 15. Or the number 3. It's a sheer wall in the fitness landscape. The organism can't make the leap.
That's the Hamming wall. So gray coding is an alternative binary numbering system designed specifically to dismantle those walls. In gray code, the numerical alphabet is rewritten so that any 2 successive numbers differ by only a single bit.
Oh, wow. So moving from a 7 to an 8 only requires one tiny mutation.
Right. It smooths out the massive leaps into a gentle staircase, making it much easier for the algorithm to inch its way toward a better solution without getting stuck.
Seeing all these clever variants, adaptive GAs, elitism, gray coding, it becomes really clear that this isn't just pseudobiology voodoo. It is a highly refined mathematical tool. And it's worth noting that the timeline of this tool's development is astonishing. I mean, this idea of computational evolution is deeply foundational to computer science.
It really is. Alan Turing, who is widely considered the father of modern computing, proposed the concept of an evolutionary learning machine in his papers back in 1950.
1950.
Yeah. And by 1954, a scientist named Nils Baricelli was actually running computer simulations of evolution at the Institute for Advanced Study in Princeton.
Consider the context of 1954 for you listening. They were working with massive room-sized machines that relied on punch cards and vacuum tubes. They barely had functional screens or memory storage, yet they were already attempting to encode Darwinian evolution into silicon.
The theory was sound 70 years ago. It just took decades for hardware processing power to finally catch up to the vision.
The persistence of the idea speaks to its underlying power. It offers a paradigm shift in how we approach problem solving.
It absolutely does.
If you take away one mental model from this deep dive, let it be this. Genetic algorithms remind us that sometimes the best way to solve a staggeringly complex challenge is not to meticulously design the perfect solution from the top down. It is to design the conditions for the perfect solution to emerge on its own.
Right.
It's about setting the rules of survival, letting go of absolute control, and allowing iteration and time to do the heavy lifting.
That is the ultimate value of the genetic algorithm. But before we finish, the source material notes one final critical limitation regarding dynamic data sets that I think leaves us with a pretty profound question about the systems we rely on every day.
Right. How do genetic algorithms handle an environment that is constantly changing?
They struggle immensely. Genetic algorithms are incredibly effective at finding a permanent solution for a static problem. The genomes converge early on toward a highly optimized shape or route for the exact data they have right now.
Okay, but what if that environment suddenly shifts?
If the rules of the game change after the population is already converged, that highly evolved solution becomes entirely invalid.
So all that work is just wiped out.
Basically, developers try to patch this with techniques like triggered hypermutation, which is basically injecting chaos back into the system, or by dropping random immigrants into the gene pool to force new traits.
But the core vulnerability remains. The organism is perfected for yesterday's environment.
Think about how heavily our modern world relies on dynamic data. Supply chains, traffic routing software, financial markets. These are environments that change by the second.
If we're relying on highly optimized, evolved algorithms to run the logistics of, say, a grocery store chain, and a sudden weather event completely changes the shipping routes, the system might completely break down.
It could.
It makes you wonder about the fragility of perfect optimization. If the environment suddenly changes, will these digital organisms running our infrastructure be able to adapt in time? Or, because they've already locked in their genetic traits to be absolutely perfect for a world that no longer exists, are they doomed to immediate extinction?
It's a scary thought.
Picture that twisted, mangled NASA antenna again. It's the absolute perfect, flawless shape to transmit data in the exact atmospheric conditions it was evolved for. But if the atmosphere changes, it's just a bent piece of metal. Something for you to consider as you navigate the highly optimized, ever-changing systems in your own life. Thanks for joining us on this deep dive.